Welcome to Introduction to Formal Logic. Very excited to get this course started. This is the first lesson. So let me make just a couple introductory comments that will apply to this lesson, but it's also going to apply to other lessons as well. So this is obviously a video format, and that means you have the freedom to pause, you can rewind, you can watch things a couple times if you don't understand the explanation right away, if you zone out, if someone interrupts you. So feel free to make this lesson and the rest of the lessons work at your own pace. Part of the advantage of doing something like this that is asynchronous is you have the control, you have the freedom to do what you want in terms of pacing. And don't worry, we're going to go slow. I'm going to try to explain everything step by step, but it's really important that before you move on to another step, you get the step that we're talking about at the moment. Logic is the kind of thing that really builds on concepts and skills. And so you don't want to move on to the next material before you really master the material at hand. All right, so that works for a lot of topics, but really in logic, you want to remember that you've got to master something before you move on. All right, so you'll see what I mean as we go through the material. So let's get started. Let's look at the outcomes that you can expect from this lesson. There are just a few. So because logic is a language, it's expressed through a language, which is obvious, we'll start by going over some basic ideas from the philosophy of language so that we can identify the parts of language that we're talking about and how they function. You'll see as we develop this lesson that it's going to be important for us to identify and categorize and label parts of language so that we can easily refer to those parts of this logical language later on. So that's what we're going to be doing. That's what you can expect. You're going to learn in this lesson what an operator is and how all the operators of propositional logic, that's what we call it, how they work or how they function and what they mean. All right, so that's important. There's a lot packed into that, how they function, how they work, and also what they mean. Okay, so with those introductory comments, let's dive into our first lesson. This lesson on operators. Let's get this down so that we can then apply it to later exercises and lessons. All right, so statements, sentences, and propositions. So let's start with something that's very obvious, really easy to get us started. All right, so the following that I'm going to put up on the screen here is a sentence. The cat is on the mat. Really basic. That's going to be a sentence, right? And you know that already. What I want to point out here is that the objects that you see on the screen and here, the black pixels that you see on your screen, and also the sound waves that I'm producing from my mouth, those are objects, black pixels, right? If you could just observe them outside this context and go, there's some black pixels and I'm hearing some sounds. Those are objects in the world and they represent some other things in the world. In this case, in this sentence, some cat, a mat, and how those things are related. All right, so that's the basic principle that we're starting with. There's some things in the world, like black pixels on a screen, or sounds coming out of my mouth, vibrations, sounds coming out of my mouth, and we let those things represent some other things out in the world, all right? Some objects that represent some other objects or things, let's say. So statements like the one above that I put, the cat is on the mat, they can be, for our purposes, true or false. And again, for our purposes in learning classical logic here, that's what we're going to be focusing on and learning is classical logic. Statements cannot be true and false in the language that we're going to be talking about, classical logic. They also can't be neither true nor false. All right, so they can't be both true or false. They can't be neither true nor false. All right, so that's going to be one of the first rules that we get down. And that's a rule that is within what we call classical logic. Other kinds of logics really, sometimes they relax that rule. All right, but we won't need to talk about that. Those are non-classical logics and we won't be dealing with that here. So also for our purposes, we're only going to be dealing with a particular part of ordinary language. Statements or sentences that can be true or false. So language can express all kinds of different things. And we're going to be only concerned with the part of language that includes statements that can be true or false, all right? Rather than other expressions like wow, an exclamation, or close the door, which is just a command. Those kinds of expressions cannot be true or false. So for our purposes, we're not going to be concentrating on those. We're going to be concentrating only on the parts of language that can be either true or false, and not both and not neither. All right, so basic groundwork here just to get us started. Here's a little bit more terminology. So a proposition, right? You've heard that word before. Maybe you're not familiar with it. Maybe you're a little familiar with it. A proposition is the thing, whatever that is, that can be expressed in different ways in the same language, and we'll talk about that. And it can also be expressed across multiple languages as well. All right, so here's an example. We're going to look at a couple examples that demonstrate both ways, expressed within in different ways in the same language, and also this thing that can be expressed across multiple languages. Okay, so here's an example. I'm holding my coffee cup in my right hand. That's an example of a statement, just like the cat is on the mat that we looked at before. And right now it's false, right? Because reality doesn't reflect that that's the case. Okay, so now it's true. Now it's true. All right. Okay, I'm holding my coffee cup in my right hand. That's the example. But I can express the same proposition that the statement above expresses, but I can do that in a different way. Here's how. What if I said, in my right hand, I'm holding my coffee cup? Okay, it's similar, but it's different. And so how are we going to think about that in terms of language? Well, we want to say that in some sense, those different statements, they're different in terms of word order, those sorts of things. They're different in that way, but they express the same thing. So the similarity there, we want to say it's the same proposition that's expressed in just different ways. So the thing that is in common with those two similar but different statements, it's not something physical. It's not something that you can touch or feel or weigh, right? It's abstract, we call it. And philosophers call that thing that is expressed in different ways a proposition. Okay, so that's what we mean by proposition. It's this thing that can be expressed in different ways. Okay, so here's another example. We saw how a proposition can be expressed in different ways within the same language, English, which you're familiar with. So here's another example. That example that I'm putting up there on the screen. Thanks to Google Translate, that's what I used. There, the same proposition is expressed in modern Greek. All right, and I don't know that well enough to demonstrate how that's the case. I really just used Google Translate. But I'm holding my coffee cup in my right hand, or whatever the particulars were. That can be expressed in modern Greek. All right, here it is in Nepali. Very different characters. It looks completely different in terms of just the visual appearance, right? So this is how we want to talk about the similarities and differences within language. Those things up there, those look different, right? Visually, physically, those are different things. They look very different from I'm holding my coffee cup in my right hand. That's the English expression that we started out with. But if there is anything in common between statements that express the same thing, it's not going to be the visual appearance. It's not going to be like word order or something like that. We say that whatever those things have in common is that they are all expressing the same proposition. Okay, so we've gone over that, but here's a natural question you might have at this point. What does all of this have to do with logic? Why am I going through these basic principles of what language is and how it can be expressed and what a proposition is? Well, we're going to be learning what's called propositional logic, where the most basic units, the most basic parts or units of the language of propositional logic, they're going to be statements or sentences or propositions. All right, for our purposes, those are going to be the same thing. We can make distinctions if we wanted to get into the greater details of philosophy of language, but we're not going to do that here. So in fact, other names for this kind of logic that we're going to be studying, other names are statement logic or sentential logic. And you see the term there. There's propositions, there's statements, and there's sentences. And again, for our purposes, those are going to be similar enough where we want to treat them the same way. So because we can express a single proposition in many kinds of ways within a single language, and as we saw, across multiple languages as well, propositional logic chooses to express a proposition that is as complex as you'd like, using a stock of familiar symbols, some symbols that will be familiar to you, others that might not. And an example of that is just the letter P. So in propositional logic, we can use just single letters to represent very complex things, right? Just like in ordinary language, we use all kinds of objects to express other things in the world, right? Okay. So we could shorten or abbreviate or represent "the cat is on the mat," that sentence that we started out with, by letting P represent that statement. All right, so that's one of the things that our logical language allows and often does, is let a single letter represent a much more complex sentence or proposition. So in that way, we can temporarily let something very simple, like just one letter, represent something that's very, very complex. So in propositional logic, there are all kinds of reasons why we want to shorten and simplify statements, and you're going to see these reasons as we go along. All right, but just to sort of preview it, it's so much easier to keep track of mentally, to kind of conceptually keep track of a single letter than a very long sentence. And it also shortens just what you have to write and manipulate. So it's much more efficient in that way. We can do so many more things with just a single letter more quickly and let it represent something very complex. We can just do a lot more things with it. All right, so that's one of the reasons why we do what we do in this language. All right, so let's talk about operators or connectives. You might see the word operator, instead of the word operator, the word connective used in other logic textbooks. Again, those are going to be pretty synonymous. All right, so let's get into it. So let's say that P, just the letter P, represents "you made an A on the final." All right, so P is going to represent that statement. And then we're also going to let Q represent the statement "you passed the class." All right, so far you're keeping track of just a couple different statements. You made an A on the final, and we're going to let P represent that statement. And then the second statement, "you passed the class," we're going to let Q represent that. All right, so we've shortened it to just a couple different letters at this point. Now we can talk about all kinds of relations between the two. So in propositional logic, we sometimes use P, Q, R from the alphabet for what we call propositional variables. And it's just sort of custom that we use P, Q, and R pretty regularly. You don't have to. Other textbooks might use from other parts of the alphabet. You might have seen that. But typically we use P, Q, and R because that's just been the custom, where this part of the alphabet, like P, Q, R, we have sort of designated that in some cases to let those letters represent propositions. All right, proposition variables. They represent propositions. And because they are variables, as opposed to what we also call constants with a fixed meaning, they can represent any proposition at any point. So variables can represent all kinds of different things within its use at a given time. So for example, let's look at a couple ways that we can connect those two statements that we saw above. Remember the two statements: you made an A on the final, it's one statement, and then you passed the class, second statement. Now we can connect them in the following way. You made an A on the final, that was the first statement, and There's our connective. There's going to be our operator. There's going to be a second statement. You pass the class. They're connected by and. Okay, I know we're starting out simple, but we want to get this down because these principles will come up again and again and again. So you made an A on the final and you passed the class. That connects the two statements above by and. Now we've made a longer sentence than just the one and just the two. We've combined them and we've connected them. Here's one. If you made an A on the final, then you pass the class. That's going to be a different kind of connection going on between the one sentence and the second sentence, right? It connects the two statements that we've already seen by an if-then clause. So we had a stock of a couple sentences, right? 1, 2. You made it on the final. We'll represent that by P. You pass the class. Represent that by Q. And we can connect them in a couple different ways that we've seen. We can connect them through and that's going to mean something. And we can connect them through an if-then clause. And that's going to mean something different, right? Okay. When we have just a propositional variable by itself, like P, what we call that is a simple sentence, or what I'll refer to as an atomic sentence. Why do we call it an atomic sentence? It's not because it's it explodes or something like that. It's because in ancient Greek, something was atomic or atomos if it couldn't be split or divided into further parts. All right, so think of it as the simplest thing possible. It can't be split or divided. And that's how we need to think about atomic sentences. Atomic sentences, it's just one sentence that can't be divided into further sentences. So we're going to label those kinds of sentences with a certain label that we call atomic sentences. All right. And this is important because we can build more complex sentences out of one or more atomic sentences, which we call compound sentences. So you might think of it as sort of molecular sentences, if that helps. Like we build more complex sentences with either several atomic sentences connected in some way, or you'll see another way is one atomic sentence that has an operator attached to it. So a compound sentence, what does that mean? It has more than just an atomic sentence as one of its parts. That's all. It has more than just one atomic sentence as one of its parts. And so there are a couple of ways to do that, to sort of add on to this one atomic sentence, whatever that atomic sentence is. So for example, we've looked at this statement before. You made an A on the final and you passed the class. That's an example of a compound sentence because it has two atomic sentences and a connective for its component parts, right? So we have a couple different atomic sentences and we combine them by an operator or a connective. It connects the two. And that's why I tried to explain it as sort of simply as possible before. This is an important principle. Here's another example. It's not the case that you made an A on the final. There's another sentence. That's another example of a compound sentence. And why? Because it can be broken into more than one part. You have the atomic sentence, but then you also have the negation part. So it can be divided. It can be split. The atomic sentence itself and also the negation part. So for our purposes, it is not the case that is going to be represented by an operator symbol in our logic language, and that's that squiggly line. We call that the tilde. Other textbooks use that other like bar with a little like vertical part of the bar, that symbol that you see there. Other textbooks use that. I'm going to use the tilde, the squiggly line, because it's actually a character on your keyboard. So we can express more complex sentences and statements like that squiggle P. That's going to mean not P, or it's going to mean it is not the case that P. All right, so it has a couple different English equivalent translations. You can translate that not P as not P, or it is not the case that P. Both of those are completely legitimate translations. And we said earlier that, at least for now, P can mean you made an A on the final. All right, so that's what we're going with temporarily for our purposes. We can also negate any sentence that you want. Any sentence can be negated, no matter how complex. And we can even pile on as many negations as we want, like you see there. 1, 2, 3, 4, 5, 6 negations. So not, P. And that sentence will still be meaningful. It'll be awkward. We usually don't want to do that sort of thing. But the point is the rules, what we call the syntax, allows for that to happen. And the semantics also allow for that to happen so that we can interpret that properly. It does have a meaning. It's an awkward meaning, but it still has a meaning. All right, so we don't want to do that, but I just want to flag here that it's possible to do that in the language. You might see especially like a double negation. And the principle is that you can have triple negation or quadruple negation. Again, usually we don't want to do that, but it does allow for it. So learning these symbols, right? There's one symbol that you typically don't use in ordinary language. That's the tilde, the squiggly line. Learning these kinds of symbols initially might look a little foreign, but the learning of different symbols just shouldn't be too difficult at this level conceptually, because you have already seen symbols like these in basic math when you learn just basic arithmetic. So if you know what the symbol for means, for example, and you know that a dash next to a number symbolizes a negative number, you know that that thing right there, not 4, or -4 really, means -4. All right, it's the same sort of principle. You've done this before. It's just you're learning a couple different rules for the specifics within our logical language. But you've already done that for basic math, basic arithmetic. You also know what that symbol means, plus sign. And when that plus sign has a number on either side of it, you just add those numbers up and it's going to spit out its numerical equivalent, right? So you know the rules of this plus symbol, and we can call it an operator, and you know how to put it together so that when it operates, when it sort of does its thing or its function, you know the equivalent. All right, so we're doing something very similar here. You already know how operators work because you learned how to use them as a kid when you just learned basic arithmetic. You may just not have thought about it in this way yet, but as we learn logic, there will be a lot of similarities to what you learned in basic arithmetic. You're going to be learning operators, but you've already done that. You're going to be learning the rules for them. You've already done that in basic arithmetic. It's just going to be the specifics that will be a little bit different. All right. So you've done this kind of thing before. It's going to eventually be second nature to you. All right. So we've talked about some rules in logic, just a couple of them. Now let's talk about the semantics or the meanings. So the meanings or the semantics, you can think of those as just interpretations. When you hear semantics, think of meaning, think of interpretation. The meanings of those operators are going to be a little different from how you think of meaning in ordinary languages. All right, so even the idea of meaning is going to have a different sense in propositional logic than it does in just ordinary language. So the meanings in propositional logic, the kind that we're going to be taking a look at, those are going to be based on what we call truth value, whether a sentence is true or false. So the meanings in our propositional logic language are going to be tied to truth values. All right, and that's going to be different. So here's an example. The meaning of that negation operator, that squiggly line, the tilde, the meaning is that it flips the truth value of the sentence that's being negated. In that sense, it's very similar to English not, right? There's a close sort of semantics or interpretation between ordinary language, something like English, and our logical language that we're taking a look at. So flipping a truth value, that work that's involved is what we call a function. And generally, a function takes some amount of inputs, you input, like a sentence in our case, like there's the input, and then the function goes to work and gives you one output, like for our purposes, a truth value. That's how functions work. All right. On a basic level, that's how functions work for propositional logic. A function, if it helps, you can think of it like a juicer. All right. You have some inputs, like maybe you're going to put celery in, or you're going to put carrots in, or something like that. Right. Those are going to be like your inputs. You press that in to this machine, this functional thing. And then the juicer does its thing, like it functions, right? And then you get some sort of output. You get one output, the juice. And you can put all kinds of inputs in. You can put celery, carrots, whatever else, and you're just going to get one output. In this analogy, it's juice. In our case, for propositional logic, it's going to be a truth value. You're going to get either true or you're going to get false. And that's it, depending on the inputs. So the single meaning of all these operators it's never going to change. For the AND operator, it has one and only one meaning, and that meaning will never change. For the OR operator, we'll see all this coming up. It's going to have one meaning, and that meaning will never change. Sometimes operators are called logical constants for that reason. The meanings are constant. They just don't change. They're fixed. There are a lot of important reasons for that. They will always be defined in the same way by their function with truth values. That's going to be their definition. And so for that reason, we call them truth functional. That's why we call them truth functional. All right, so you might hear that term coming up. Now you know the reason. So if I have an input that's just P, all right, that would be like the celery in our analogy, and P is true, then the function of negation goes to work, it does its thing, it functions. And what does it do? Well, its meaning is it flips that truth value from one case to the other. In this case, from true to false as its output. So false is going to be its output. The function is going to do the work. It's going to have an output. And in this case, it's going to be false. That will be the output. So that not P is false if P is true. You see there, all right? So it's kind of a long-winded way of saying it just flips the truth value from false to true, from true to false. Okay, but we want to get the principles down so that we can apply them to more complex situations later. All right, truth functional operators. Let's talk about negation. We mentioned some principles before. Let's look at it a little bit more closely. If you didn't catch every bit of that description, that's okay. We're sort of zooming out and looking at the very broad principles at this level to set a foundation for looking at more specifics later. We're going to see how it works when we actually do some problems. We'll talk about the problems later. And we're going to get more specific on the meaning of our 5 operators. All right, so let's take a look at that. For now, let's look at other operators for propositional logic. We looked at negation and a few things, and we're going to look at how to interpret them. All right, so you're already familiar with our first operator, that squiggly line, the tilde. It's for negation. You might see it in some logic books as that other symbol there. I'm going to use, as I said, the tilde just because it's easy to type. It's really easy. It's the key in the upper left of the keyboard. So you don't have to have some sort of like special symbol. You don't have to go to that part. All right, so it's just the tilde. You'll see it, the upper left of the keyboard, shift and that character, and you're set. You can write negation in logic. So let's say you made an A on the final is represented by P again. All right, so we're going to do that same thing that we did earlier. We're going to have the same stock sentence, you made it on the final, and we're going to have our representative letter, P, that's going to represent that statement again. Okay, so if it's in the context of negation, if it's true that P, all right, in reality, you did make an A on the final, if that's true, then not P is going to be false, because what does not P mean here? Well, it means it's not the case that you made an A on the final. And that's not right if you actually did, right? It's false. We want to say it's false. Very basic. If it's false that P, the fact of the matter is that you actually did not make an A on the final. If that's the case, then not P, or the statement, it's not the case that you made an A on the final, then it's going to be true. All right? Very basic of how negation works, starting slow. If you didn't follow that, then go back and make sure that you're tracking with the truth values and negation. But again, the basic point is that negation flips the truth value. All right, that's the most important part. Now we're going to talk about conjunction. All right, this is going to operate a little bit differently. The function is going to be different, but we're going to take this step by step too. And the same thing with the rest of the operators. So the conjunction operator is a little different from the conjunctions that you learned about in English class and basic grammar class. For our logical language, it's going to connect multiple statements. All right, so there's a similarity, but it does it in a very specific way. And here's what I mean. A conjunction sentence, a sentence whose main operator is the conjunction operator. And I'll talk about what a main operator means in a second. It's going to be true if and only if all of its conjuncts are true. And it's going to be false if even one of its conjuncts is false. All right, so that's how we're going to think about the conjunction operator. All right, so here's an example. Let's take a look at an example, and then I'll explain a couple of those things. For propositional logic, here are our familiar statements again. You made an A on the final, and you passed the class. That's going to be true. That complex statement that has two atomic statements and an operator, which is and, conjunction, it's going to be true if and only if both atomic sentences, you made an A on the final and you passed the class, if both of those are true. If any of its parts, if either part in this case, which we call a conjunct, is false, then the whole sentence is false. All right? So let that be one of the principles that you memorize at this point. All right? For conjunction, it needs each sentence, which we can label a conjunct in this context. All right? So if the main operator in a sentence is conjunction, then its parts are going to be what we call conjuncts. Those are the atomic sentences that we also put another label on, which is conjunct, if that atomic sentence is part of a compound sentence that has a conjunction operator. All right? So you already have a lot of terminology that you're dealing with. So make sure that you're getting every part of what I'm saying at this point. Remember, we're labeling parts of language at this level so that we can use those labels later on, and we can be really efficient and quick with how we talk about logic and language. All right, so make sure that you get this point. All right, so I talked about a main operator. Just a quick point of explanation. Sometimes compound sentences are going to have more than one operator. And later on, I'll show you how to identify what the main operator is within a sentence. All right, but the reason that we specify the main operator when we're doing our definition here in this second point is because sometimes a sentence can have a lot of different operators. And when the conjunction operator is the main one, then that's going to be a conjunction sentence. All right, even though it might have a lot of other operators within it. And you'll see what I mean later on. So maybe it's helpful. Think of a conjunction as being very strict when it comes to truth. All of its conjuncts have to be true for the whole sentence to be true. All of them. If there's only one conjunct that's false, the whole thing is false. All right? So we can't have any falsity if we want our whole statement to be true. So we're going to represent and conjunction by that symbol that you see there. It looks like an upside down V, a little mountaintop. In some logic books, you might see it different ways, like what's called the ampersand, that other sort of like design thing, or you might see it as just this dot this sort of like floating dot. Other textbooks use those symbols to represent conjunction or and, but I'm going to go with that upside down V. I'm more familiar with it, and I want to choose something that looks a little bit easier. So, and also it has some symmetry with the disjunction operator, and you'll see that. So in the following sentence, you made an A on the final, and you passed the class, and you're cleared to graduate. There's going to be our sentence. And you can see there it has a couple different operators, right? All of those individual atomic sentences need to be true for the entire compound sentence to be true. All right? Each of its parts needs to be true for the whole sentence to be true. So later on, we're going to use visual, what we call truth tables, to see in a different way how all of this works together. And we're going to use truth tables because it lays it out in this visual way that helps us understand how they function. And it's a very common way of understanding how these operators work in a simple way with more complex statements. All right, so just to flag that we're going to be using truth tables to see how all this works coming up. For now, we're just getting down the principles and the context for interpreting our logical language. All right, so we've talked about negation, we've talked about and or conjunction. Now we're going to talk about disjunction. There'll be some similarities and differences with conjunction. Okay, so the disjunction operator is also a little different from the English word or. We're going to translate it as or, but it's not going to be the exact same or that we say in English. It also can connect multiple statements, but as we said before, it means something very specific in our propositional logic language. So for our language, a disjunction sentence, a sentence whose main operator is the disjunction operator, it's going to be true if and only if at least one of its disjuncts are true. And it's going to be false if all of its disjuncts are false. Okay, so let's look at an example so that you know what we mean. For propositional logic, familiar sentence again, but this time the operator is changed. You made an A on the final, one atomic sentence, or operator, you passed the class, another atomic sentence. So you see how that's a compound sentence. That's going to be true. That compound sentence is going to be true if and only if any of the following disjuncts are true. You made an A on the final. If that one's true as part of that whole statement, then the whole statement's going to be true. Or if you pass the class, if that's true, then in the compound statement, the whole compound statement's going to be true. All right. It only needs one. If all of its parts, and in this case we call them disjuncts, are false, the whole sentence is false. All right. If all the parts, if all the disjuncts of a disjunction sentence are false, then the whole sentence is false. Otherwise, if we even have one disjunct that's true, the whole compound sentence is true. That's the way that disjunction works or functions. So in contrast to conjunction, think of a disjunction as being very lenient when it comes to truth. Any of its disjuncts can be true, and then the whole sentence is true. All right. So again, this is the truth functional part of logic, right? The function is going to spit out a truth value. If even one of its disjuncts, its atomic sentence that we call disjuncts, if that is true as a part, then the whole compound sentence is going to be true. That's the way it works. That's the way it functions. So notice also that the form of a disjunctive sentence, like P or Q, right? If we extract the content and we just let some sort of meaningful sentence, like you made it on the final, if we abstract that and we just take a look at its form and represent it by just a letter like P or Q, all of the parts or disjuncts can be true. And the reason I'm pointing this out is because this has a name as well. So here's a little bit more terminology for you. We call this inclusive disjunction. In contrast to another kind of disjunction, which we call exclusive disjunction. So let me talk about the differences between inclusive disjunction, which is the one that we're going to go with. We're going to assume inclusive disjunction, but it's in contrast to exclusive disjunction. All right, so exclusive disjunction only allows one or the other disjunct to be true, not both. So in exclusive disjunction, only one disjunct can be true, not all or both. All right. On this interpretation of or disjunction, in the sentence P or Q, either P is true or Q is true, but not both P and Q. That's exclusive disjunction. That's not going to be the interpretation of or disjunction that we're going to go with. For our inclusive interpretation of or, all disjuncts can be true. And so this intuitively makes sense because sometimes we have a sentence like, I have on black pants or I have on a white shirt. That sentence, I have on black pants or I have on a white shirt. That can have all true disjuncts, right? That's obvious. I can have both of those things be true at the same time. Sometimes, though, the content of a disjunctive sentence in English makes two disjuncts mutually exclusive. Like, for example, I will be home or I'll be at the store. That's an example where only one or the other can be true. You can't be in two places at once, right? You can't say, oh, well, I'm at home and at the store, unless you live at the store, but all things being equal. So we're going to let the content of the sentence determine when that's the case, right? When both of those exclude each other, when they exclude each other, the content, not the form of the sentence. All right. So you'll see that later on, but that's an explanation that I want to give you where if you're wondering, okay, why are we going with this interpretation of or rather than the exclusive kind? This is why. Okay. So we're going to represent or. Let's talk about the symbol now. Disjunction by that symbol right there. It looks like a V, but it's a little different than the English alphabet character V. All right, it's the upside down version of and or conjunction. So in the following sentence, which should be familiar by now, here's the big sentence. You made an A on the final, one atomic sentence, or operator, disjunction. You passed the class, atomic sentence, or another operator. You are cleared to graduate, atomic sentence. And remember that all those parts, we call them disjuncts. There's the big long sentence, and I labeled it for you. Any of those individual atomic sentences can be true for the whole compound sentence to be true. You only need one. It could be the first one, the second one, or the third one. If any of those are true, then the whole thing is true. If all of them are true, the whole thing is true. If two are true, the whole thing is true, right? So the same will be true in this sentence. This is a weird sentence. First atomic statement, 2 plus 2 equals 4. And then operator, or. Second atomic sentence, or disjunct. All dogs are reptiles. And then we have another operator, or. Some circles are square. All right, that's a weird sentence, but our logical language allows us to do that. So how are we supposed to think about that weird sentence? Well, the first disjunct, which is 2 plus 2 equals 4, that's true, of course. 2 plus 2 equals 4 is true. So that makes that whole weird, complex, compound sentence true because all you need is one. And we got that on that first atomic sentence. As weird as that seems, that's how or is going to work in propositional logic or a logical language. All right. So I want to flag the difference between how we ordinarily express things in English. We're going to be expressing some different things, maybe some weird things in our logical language. So again, later on, we're going to use truth tables to see how all of this works for disjunction and all the other operators. All right, we're going to get more specific, and there will be problems that come with that, problem exercises that come with that. Okay, now let's take a look at conditionals. And conditionals are going to work a little in a degree that's more different than ordinary English, than what we saw for negation, conjunction, and disjunction. All right, so there are two kinds of conditional operators in propositional logic. There's just the conditional, and we'll talk about that, and then there's the biconditional, and we'll talk about that separately. All right, so two kinds of conditionals. The conditional operator, it can mean something pretty substantially different from the English phrase if then. That's the basic English translation of the conditional. If something, then something. And the conditional operator connects two sentences. So a conditional sentence, here's the definition of this sentence. A conditional sentence, a sentence whose main operator is the conditional operator, will be false if the first part, which we'll call the antecedent, we call that the antecedent, that's the first part of a conditional, is true. If that's true, and the second part, which we call the consequent, is false. Otherwise, it's going to be true. All right, so that's another point, definition, that you need to lock in your brain. A conditional sentence will be false if the first part, the antecedent, is true, and also the second part, which we call the consequent, is false. That's when the conditional is false. Otherwise, it's going to be true. Okay, so here's an example. You'll see why I phrase it that way. For propositional logic, another familiar sentence here, if you made an A on the final, then you pass the class. That's a conditional sentence. That's going to be false if and only if the first part, the antecedent, you made an A on the final, that's the antecedent part of the conditional. Again, this is why labels of language are so important. All right, we're going to label the first part of a conditional the antecedent. So remember that. First part of a conditional is called the antecedent, and I'll be referring to that throughout this lesson and the whole course. All right, so I interrupted myself. For propositional logic, that conditional, if you made an A on the final, then you pass the class, it's going to be false if and only if that first part, you made an A on the final, the antecedent, is true, and you pass the class, that second part, the consequent, is false. Otherwise, in any other truth value combination, the whole statement is going to be true. All right, so we're going to look at this in detail. I'll show you. The meaning of the conditional, the way that its truth values work, it's far less intuitive than negation, conjunction, and disjunction. So just know that going in. All right, the conditional is going to have instances that might sound a little bit weird because you're used to the conditional working in a way in English, and it's not always going to work that same way in our logical language. All right, so I'll explain. Here's how it goes. We typically think that in English, there's some sort of like causal connection between the parts of conditional statements, like if you made an A on the final, then you pass the class. Right? If we say that, then making an A on the final in some sense caused a passing grade. Or you can think of it this way, like if I don't have one here, but like how about this? We can say something like this, right? Here is a pen. If I drop the pen, then it will fall to the ground. It did. All right. So there's some sort of like causal relation there between the antecedent, the first part, and the second part, the consequent. All right. Ordinarily, we use conditional statements that way. Or for example, if I say, if I'm in the philosophy building, then I'm on campus. There's a sense in which being in the philosophy building in this scenario, this hypothetical scenario that I'm talking about, being in the philosophy building in this scenario naturally implies that I'm on campus. If the philosophy building is on campus, right? In that scenario, there's some sort of causal connection that we sort of assume. That's the ordinary way that we use conditionals for the most part. And so that causal relation will sometimes be represented in our logical language by the conditional, but not always. There will be other kind of weird cases. So the relation that the conditional symbol, we're going to get to that the conditional symbol represents is what we call material implication. That's not going to be super crucial for you to know at this point, but it's important to know if you want to fill out your understanding of what the conditional means. This term, the relation is called material implication. So like I said, it's not all that important at this point for you to know this term, material implication, but you should know its name so that later on you can distinguish it from a different kind of implication. All right, so I just want to cover that as completely as I can here, but at this stage, it's not going to be super crucial for you to know this term, material implication. Okay, so having said all that, I pointed out that there are weird aspects to the conditional. Weird in the sense that they don't follow the English ordinary usages like you might be used to. So what is the weird part of a conditional sentence that I've been referring to, or what we call the material implication relation? Well, remember that a conditional sentence, a sentence whose main operator is the conditional operator, it's going to be false if the first part, which we call the antecedent again, is true, and at the same time, the second part, called the consequent, is false. In any other case, it's going to be true. The whole statement's going to be true. So what does that mean? It means that the conditional can sometimes do weird things that we aren't used to in English. So it means a statement like, if the local football team is undefeated, 5 is an odd number, that statement will always be true because there's no possibility that the consequent, that second part, 5 is an odd number, will be false. And again, it doesn't look like there's any sort of causal there isn't any sort of causal connection between a local football team being undefeated and 5 being an odd number. But the way that our operators work in propositional logic is really different from English. So in our logical language, it works. Okay, so it sounds strange in English, again, because of the way that conditionals are interpreted in English, the way that we use them, having some sort of causal relation as ordinarily part of its meaning. But remember that propositional logic gives what we call a truth functional meaning to sentences in its language. It's the truth value that we think is important, that we highlight. That's its function. So those meanings won't always match perfectly with English meanings. All right, so know that going in. There are going to be some, like I said, weird things that happen, but they're weird only because it's going to be a different interpretation in our logical language. Logicians have stuck with this interpretation of the conditional because of how well it works in logic, not because it always matches how we use a conditional in English. All right, so you'll see that later on, how the conditional actually works. So here's an example that many logicians use to explain how the meaning of the conditional in logic can, at least in this case, be similar to its meaning in English. It won't always be similar to the English meaning, or really how a connective works, how the conditional works in English. But here's one way to sort of demonstrate that, at least in this case, it's pretty similar to English. It can be similar. So take our familiar statement you've seen before. If you made an A on the final, then you pass the class. And let's say that I did actually make that promise to you. I said that and I promised that to you. So in that scenario, in that instance, if it's true that you made an A on the final and it's false that you passed the class, well, then the whole sentence is false. I broke my promise. All right, so we know the first part because of the way the conditional works. If the first part is true, second part is false, the whole sentence is false. And in that sense, I broke my promise. But if it's true that you made an A on the final and it's true that you passed the class, the whole sentence is true. So in that sense, I kept my promise. Okay, what about if it's false that you made an A on the final and it's false that you passed the class? The whole sentence is still true. I still kept my promise. It's just false that you made an A on the final, right? And then the last, if it's false that you made an A on the final and it's true that you passed the class, the whole sentence is still true. I still kept my promise because the condition of making an A in this case doesn't apply. All right, so if that's helpful, great. It's one way that an example in English can kind of track the meaning of the conditional. If that's not that helpful, that's okay. But it's used again to illustrate how, at least in one case, the meaning of the conditional in logic tracks similarly to the meaning in English. All right, but that won't always be the case. All right, we're going to come back to the semantics or the meaning, the interpretation of the conditional later. Hopefully you get the point by now that it's a little different from the way it works in English. Sometimes it can be a lot different. So we represent, what's the symbol? We represent if then, the conditional, by that symbol. It's this arrow. In other textbooks, you might see it as the horseshoe. All right, so both of those really mean the same thing. In my case, I'm going to stick with the arrow. So here's a sentence. If you made an A on the final, then you pass the class. Very familiar. The first atomic sentence must be true. And the second atomic sentence must be false for the whole compound sentence to be false. Otherwise, that whole statement is true. So that's what you want to think about, is when you're thinking about a conditional, you want to say, okay, what's the one condition where a conditional is false? Now you know, antecedent true, consequent false. That's the one condition. That's the only time that it can be false. All right. So remember, there are actually two kinds of conditional operators in propositional logic. There's the conditional, which we already looked at, and then there's this last operator called the biconditional. Now, how does this work? The biconditional can also mean something different from the translated English equivalent phrase. This is the translation of the biconditional in English. It's a little different. If and only if, which admittedly we almost never say. All right, let's be honest. Or it can sometimes be translated in English as just in case. And it also connects two sentences. So think of the English translation of the biconditional as if and only if. And I'll explain what that means. You've actually seen this before because the biconditional, or if and only if, is used in technical definitions in philosophy and especially logic. All right, so it also connects two sentences. Here's what I mean. A biconditional sentence, a sentence whose main operator is the biconditional operator, it's going to be true. That compound sentence is going to be true if the biconditional is the main operator, if both parts, each atomic sentence of the biconditional have the same truth value as each other. Otherwise, it will be false. All right, so if the truth value of this part and this part are true, then the whole sentence is true. If they are both false, then the biconditional is true. If there's a difference in truth value on either side, where this is true and this is false, or this is false and this is true, the biconditional sentence is false. All right, so here's an example I'll show you. For propositional logic, here's the sentence example. A person P is a bachelor if and only if P is an unmarried male. We'll take that sentence as our example. That sentence is going to be true if and only if, there's that statement again, there's that part again. If and only if P is a bachelor, that atomic sentence has the same truth value as the other part. P is an unmarried male. Either they're both true and then the biconditional is true, or they're both false and the biconditional is true. If there's a difference, if they don't match in truth value, biconditional sentence is false. That's the way it's going to work or function or operate in propositional logic. All right? Okay, in a biconditional, remember, the truth values of its two parts have to match for the whole sentence to be true. That's something you want to memorize. Just say, all right, if I'm dealing with a biconditional, it's only true if both of its parts match in truth value. Either they're both false or they're both true. That's the, yes, right. Both false or both true. That's the way that it works. Okay. So in our example that we looked at, a person P is a bachelor if and only if P is an unmarried male. There's our sentence. Think about it this way. It wouldn't make sense for P to be a bachelor, but he's not an unmarried male. That doesn't make sense because what it means to be a bachelor is to be an unmarried male, right? You can't have differently matched truth values there. And at the same time, it wouldn't make sense for P not to be a bachelor. This person's not a bachelor, but this person is also an unmarried male. That doesn't make sense either. All right. So the biconditional is set up so that when there's a mismatch there of a truth value, that doesn't quote unquote make sense. All right. It comes out false. But it does make sense that P is a bachelor and an unmarried male. And it makes sense if P is not a bachelor and not an unmarried male. All right. If both of those things are false, then yeah, the biconditional is going to be true. All right. That's how we sort of try to get at the meaning of the biconditional. But just like with the conditional, the biconditional meaning, which again is truth functional, its meaning depends on truth values of its parts. It can sometimes turn out to be weird when compared to English as well. All right. So we're going to say more about the semantics or meaning or the interpretation of the biconditional later. And we'll also talk about necessary and sufficient conditions for both the conditional and the biconditional. All right. So that's coming up. It's going to be an important concept. That concept of necessary and sufficient conditions, that's going to apply to the conditional and the biconditional and how we want to interpret it. All right, so what does the symbol look like here for the biconditional? We represent this if and only if. Again, that's our English translation. It's a little awkward, but just get that in your head. That's the way that we translate the biconditional by the symbol. It's the double arrow. Or you might see it in some logic books as that triple line there. Those horizontal lines. I will be using the double arrow for this course. That's the way that this is going to work. So in the following sentence, again, a person P is a bachelor if and only if P is an unmarried male. It's going to be true if both parts have the same truth value as each other, either both true or both false. By now, that should sound familiar. All right. Those are all the operators. That's a lot. That's a lot to process for this first lesson. I realize that. This is going to be a little bit on the longer side as far as lessons go. All right. But hopefully you stuck with all that. You've learned what an operator is in the first place and the semantics of the 5 basic operators for propositional logic. All right. That's a lot. So we really just talked about each operator and what each operator means, how they function at a zoomed out broad level. We're going to be diving into a lot more details later. These are going to be the basic building blocks for the rest of logic, the rest of this course, and really all of logic. These building blocks are used in more advanced logics like what we call predicate logic or quantified logic. That's a whole different type of logic that builds on what we're doing here. And also in modal logic that you might have heard of, which includes concepts like possibility and necessity. Also in quantified modal logic, which combines quantified logic or predicate logic and also modal logic. All right, so you don't have to know any of that, but just know that what we've covered so far are the basic, most foundational building blocks to propositional logic, which is the kind that we're going to be looking at, but also a whole lot of other logics as well. All right, so you've learned the basic building blocks for a lot of different kinds of logics. That's all for this lesson. Make sure that this is clear in your mind, that you have all of these concepts down, at least at the level that we took a look at for this lesson before you move on, and we'll do a lot more things later.